I'm going to talk about how to design photonic integrated circuits. And for obvious reasons, I think it's probably clear. I'm not going to take you through all the details in just a 2-hour session. Now, photonic integrated circuits, I guess you know, are photonic systems on a chip, and there's a lot of material systems to implement such photonic systems on a chip. And most of my work is involving silicon photonics. But so a lot of, or a number of the examples that I'm showing will be more related to silicon photonics. However, all the design principles and the methodologies that I'm going to discuss are actually valid for all types of photonic circuits. So it's not necessarily because I'm talking about a silicon photonics chip that it's going to cover just silicon. A photonic circuit is essentially a combination of functional building blocks, like a modulator, like a laser, like a wavelength filter, photodetectors, that are together connected with waveguides. Now, this is a kind of an important definition. It's a circuit. So, which means that you make a certain level of abstraction. If you talk about circuits, whether it's electronic circuits or photonic circuits, you're always talking about a set of building blocks that are connected together with signal lines. So you can abstract the functionality of your circuit as signals propagating between building blocks. This is a very stark contrast to, for instance, let's say designing a metasurface, which is a full physical structure where you basically cannot make that abstraction of a circuit with blocks connected with signals. It's both photonics, it's both on a chip, but one is a circuit, the other is not. So we're going to talk about circuits, and that means that we're going to take also a lot of the functionality, a lot of the concepts from electronics, where circuits are quite common, and take them to photonics. Now, one of the advantages of doing photonics on chips and circuits is that you benefit from a lot of the benefits that you also see in electronics. By making that abstraction and by integrating things together on a chip, you can create much more complex functionality, which basically gives you more performance, and eventually, because everything is on a chip, also lower power consumption and lower cost. Now, the functions that we're using here are very different from electronics functions. They're not transistors. Essentially, I already mentioned them. These are light generation like lasers, transport of light in waveguides, wavelength filtering, signal modulation where you take an electrical signal and encode it onto a laser line, or signal detection where you have a modulated laser line which you then convert into an electrical signal. Those are the basic functionalities of photonic circuits, and essentially it allows you to do most things that you would want to do with light. There's a few exceptions, but this is basically a lot of the functionality. Now, if you look at how these are actually implemented, today you see that all of these functions are implemented in different material systems. If you want to make a good light source, you're going to go for 3-5 semiconductors. If you want to make good waveguides, probably glasses or even polymers are very good waveguides. For modulators, you need an electro-optic material, so you're looking in materials like lithium niobate. And then for detectors, you need materials that are absorbing light. So typically it's not the same material that you use for a waveguide, where it needs to be transparent. So in most photonic, if you want to build a photonic system out of the best materials, you see that it's a very heterogeneous bunch of materials. Now, if you look at which materials are actually used in photonics today for making photonic chips, then you see that the bulk of that is dominated by semiconductors. And you see the blue box at the bottom is indium phosphide, and then the yellow box is gallium arsenide. But you also see that orange box, which is slowly growing. Actually, its growth is outpacing the other boxes, and that is silicon on insulator. And this brings us to the point of the topic of silicon photonics. Why is silicon photonics such a hype at the moment? I mean, why do we want to build photonic circuits out of silicon? Well, the main reason is not because silicon is a good material for photonics. The main reason is that with silicon photonics, you can leverage the entire fabrication infrastructure for CMOS electronics. So you basically can use a CMOS fab, an electronics fab, to make your photonic circuits. And that's a major investment that you don't need to do if you want to make silicon photonics. You don't have to build a new fab. And there's some other advantages which we'll come back to later. But essentially, the access to that manufacturing infrastructure gives you the possibility to make really complex functions at a low cost. Now, as I mentioned, silicon is not a very good optical material if you look at it for making chips. It has an indirect band gap, so building a laser out of it, forget it. It has a very high index contrast between the silicon and the surrounding silicon dioxide, so that typically means that your waveguide losses are typically higher than, for instance, in glass materials with lower index contrast. Silicon is a boring semiconductor material in the sense that it has a centrosymmetric crystal, so that means that automatically it does not have intrinsic electro-optic effects. So it makes a poor modulator. And of course, if you're using silicon as a waveguide, it should be transparent, which means that you don't have an absorption that you can use as for a photodetector. But still, silicon gives us major advantages. And you can summarize the advantage of silicon in one word, actually, scale. On one hand, we have the large-scale manufacturing that I already mentioned. But on the other hand, you have sub-micron scale waveguides. It's possible in silicon to make optical waveguides that are much smaller in size and in dimensions than a typical waveguide that people have been using for many, many years before. You can scale down your waveguide to sub-micrometer dimensions. And why is that? Well, it's mainly to do with the index contrast of silicon. If you take an optical fiber or a glass waveguide, you typically have a very low index contrast between the core that guides the light and the surrounding cladding. And as a result, your waveguide needs to be large to guide a single mode. Now, if you go to other materials like 3-5 semiconductors, you can create systems with a higher contrast. And you can scale down the waveguide to, let's say, micrometer or multi-micrometer dimension. However, in silicon, you have essentially your silicon, which has a very high refractive index, 3.5 almost, surrounded by silicon dioxide, which has a low index of 1.5. That's a massive index contrast, and that allows you to shrink your waveguide to sub-micrometer dimensions. And this shows a couple of these, like an example of these waveguides. So a typical cross-section of a silicon waveguide is about 0.5 micron wide and a couple of 100 microns thick. You can play a bit with the exact values here, but that's what you find today on most silicon photonics platforms. And if you now look at how the light is distributed inside that waveguide, you see that indeed a lot of the light is in the waveguide, but you also see that there's some light sitting outside in the cladding with a fairly high intensity on the side of the waveguide, on the sidewall. And that's something that will come back and haunt us as one of the weaknesses or difficulties in silicon photonics, and will also impose quite some constraints and difficulties on designing large-scale circuits, as I will mention later. Now, that waveguide is the most essential function on a chip. A waveguide basically transports light from one point to another on the chip, so the light propagates, but it's different from a simple electrical wire on an electrical circuit in the sense that what you have in a waveguide is literally a wave. It propagates. So there's a certain time delay and a certain phase delay of that wave as it propagates along the waveguide. So the transmission, in contrast with what people do in electronics, you cannot just assume that if 2 points are connected with a waveguide, the connection is instantaneous. So you need to describe the signals propagating through a waveguide with a certain velocity. And to complicate matters, there's actually two velocities in a waveguide that are important. On one hand, there's the phase velocity, which is essentially the crest and the crests of that optical wave, that electromagnetic wave, how those propagate through the waveguide. And that's determined by a quantity called the effective index. But in parallel, you also have a group velocity, which is essentially the speed at which a pulse or a modulated version of that wave will propagate. So the information, really the on-off, for instance, of a digital signal will propagate at a different velocity called the group velocity compared to the crests of the wave of the optical signal. So we have two quantities here, effective index and group index. And as we will see in a silicon photonic waveguide, these values are somewhat different. Now, waveguiding, of course, is not the only function you have on a chip. You need to be able to do more things with light, so you find components like splitters, where you come in with light from the left, you split it up into two parts on the right, so one input, two outputs. That means that you have like a 50% transmission from your input to both of these outputs. Now that also brings up some interesting feature of photonic circuits. You could call it a feature, you could call it a bug. It's reciprocity, in the sense that if you have a coupling from your input to an output port and that coupling is 50%, if you would reverse the flow of light and inject the light in that output port to your input, your transmission will also be only 50%. So using a splitter as a combiner is a tricky part, because the only time when you can basically get both, or get all the light from your outputs back into your input, is when you inject both outputs. You reverse all the light at the same time, so you basically inject light from your two outputs exactly in phase into your device, and then it will come back out at the input. Otherwise, your device will be inherently lossy. Now, this is actually a reason why in many photonic circuits people don't like to use these simple 1x2 splitters, because there's that intrinsic mechanism where some of the light gets lost if your two ports are not exactly in phase. So as an alternative, what is being used is what we call a 2x2 coupler, where you have two ports on each side. And now such a coupler can in principle be lossless. If the light does not go into one output port, it will end up in the other output port. So you can always recycle your light and work with your light with such a 2x2 couplers. So this is actually a quite important advice. If you design circuits, you have to be wary about how you use these couplers, because indeed you can, with a 2x2 coupler, you can really recover all of your light. Now, the most common 2x2 coupler that is actually being used today is what we call a directional coupler. It is two waveguides. You bring these two waveguides so close together that the light that is leaking out, or that is outside of your waveguide core, that little bit of light in the cladding, can actually feel the other waveguide close by and starts coupling to that other waveguide. And so by playing with the length of that coupler, you can control how much light is being coupled from one waveguide to the other. And you can tune the strength of that. You can tune the strength of that coupler by playing with the length, by playing with the gap, or by the cross-section of the waveguide. Now it becomes interesting, because we actually now have a tool which we can distribute light between two waveguides, and we have the waveguides themselves, and that already allows us to make some very interesting basic functions. For instance, if you take two directional couplers, one here and one there, and you connect them with two waveguides, but you make the waveguides a different length, you build what we call a Maxinder Interferometer. Now, this is a concept that's also known from free space optics, where you use beam splitters and mirrors, but in this case you use couplers as beam splitters and waveguides to control the path length of the light. Now, the interesting thing is that with the delay length in that path, by the time the light arrives at the second coupler, the light in the two waveguides will have a different phase delay. So it will arrive either in phase or out of phase, depending on the wavelength of the light. So we see, if we plot this as function of wavelength, the transmission in one of the outputs will go from high to low in a sinusoidal fashion, depending on the wavelength. And this is very useful, because it basically allows us to filter or to separate wavelengths from one output waveguide to the other. And likewise, you can build other circuits with directional couplers and waveguides. For instance, you can take two directional couplers and then connect them together so they form a loop. And now you have again an interferometric structure, but now the light in the loop, when it makes a full circle, when it goes all the way around and it interferes with itself, so it basically, after one round trip, it's exactly in phase with the light that is already there, then it will start to resonate, and it will end up in the top waveguide instead of the bottom waveguide. So you can make now, with such a ring resonator, a very sharp filter. You can filter out a specific wavelength line out of your spectrum for each wavelength that fits exactly in the circumference of the ring. So this is just two examples of what we would call a wavelength filter. And wavelength filters are one of the key functions on a photonic chip, and also one of the more interesting functions to actually design. And depending on what you want from a wavelength filter, you can either do a channel drop filter, so select a single band out of a wider wavelength range. You can basically separate alternate bands like into one waveguide or the other, a bit like the Maxinder Interferometer with its sinusoidal response that I showed earlier. Or you can do a multiplexer, which basically takes a spectrum and separates it into individual bands. Now, these wavelength filters all depend on the same principle. They depend on the fact that you have a delay line or multiple delay lines of light. So you basically split light up over multiple paths inside the filter. You send all these paths through a different delay, and then you combine them again interferometrically. Now, to make that work properly, these delays need to be very well controlled. And now we come to the difficulty of working with Silicon Photonics, is that the delay in these waveguides is not just determined by the length of the waveguide, but also by its effective index, by its propagation constant. And it turns out that that propagation constant in a silicon waveguide is very, but really very sensitive to the dimensions of the waveguide. So that means that we're actually operating the typical silicon waveguides on a point where the light is very much confined, it's very well tied up into the waveguide, but that also makes it very sensitive, because we saw that there was a lot of light just outside of the waveguide, just on that sidewall. So you can imagine if that sidewall moves a little bit, like with the nanometer, that will already have an appreciable effect on the propagation constant, of how much light is actually inside the silicon or outside the silicon. And likewise for thickness, if you change the thickness, your effective index, your propagation constant, will rapidly change. So if you have a fabrication process where your waveguides are not controlled very well in terms of line width, you're gonna end up with a lot of variation in the behavior of your circuit, in the behavior of your filter. So that means that when you design it, as we will come later to the design process, when you design those circuits, you need to be able to somehow assess the impact of these variabilities, of these deviations from the ideal onto your circuit design. Now, just to sketch again how important or how critical this is, if you take a wavelength filter, let's say a ring resonator or a Maxinder Interferometer, and you use waveguides there, and inside your wavelength filter, there's a variation of your wire width, of your waveguide width, with a single nanometer, the transmission band of your wavelength filter will also shift with 1 nanometer. Now, 1 nanometer in wavelength doesn't seem like a lot, but if you have a dense WDM telecommunication system where the channels are spaced 25 or 50 gigahertz, that's multiple channels. 1 nanometer then corresponds to 2 to 5 channels. So you're basically, if you want to filter out a single channel, but you're like several channels off your grid, that's not exactly what you want. Now, luckily, there's a trick that you can play. You can, instead of just making your device passive, you can add tunability. And we see that as a kind of a lucky coincidence, these silicon waveguides also have a quite high thermo-optic coefficient. So with a 10 degrees increase in temperature, you can shift it essentially back that 1 nanometer that you originally shifted due to fabrication variations. Now, the easiest way to implement such thermal tuning is by just taking a waveguide and putting a resistor on top of it or putting a resistor next to it. That's very basic. It's actually a tuning mechanism that works in almost every material system, whether it's 3-5 materials or glass materials or silicon nitride or polymers. A tuner will, most of these materials have some thermo-optic coefficient, and the tuner will essentially adjust the propagation constant and therefore the filter wavelengths of these devices. Now, typical in silicon number for a tuner is that you can induce a pi phase shift in your waveguide with between 5 and 30 milliwatts of power. If you go to other materials, that number can get higher, that number can be lower, but it's something that you have to keep in mind. Like, if you add these tuners to your circuit, essentially you're gonna run into problems where your circuits become too hot. Oh. So basically, if you want to optimize your tuners, just pick the right materials and try to isolate them as much as possible. Now, heat is only one way to electrically control your photonic circuit in some way. Another mechanism that you use to electrically influence what's going on in your circuit is modulation. Essentially, you can say that modulation is the same as tuning. You use some electrical signal to adjust the behavior of your circuit, but while tuning is usually a slow property, something that is quasi-static and that keeps your circuit in a certain desired operation point, modulation is usually intended to transmit signals. So you come in with a high-speed electrical signal that you want to encode onto your optical wave. And there's different mechanisms to do modulation. So modulation is typically much faster than tuning. And you can modulate either the amplitude of your light or the phase of your light. And there's different techniques. You can use Pockels effect materials. You can use mechanical MEMS devices. But in silicon, the most common technique that is being used today is based on carriers. Silicon does not have an intrinsic electro-optic effect, but because you have all these process technology available that is used for electronics, it's actually fairly easy to, for instance, implement a junction, a PN junction inside your waveguide, which means that you will get carriers in your waveguide, either that can be either extracted by reverse biasing your junction or injected by forward biasing your junction. And the density of carriers is directly related to the effective index, but also to the loss of the materials. So by playing with carriers in a junction that's embedded inside your waveguide, you can do rapid modulation going from, let's say, on the order of a few gigahertz with an injection modulator to tens of gigahertz with a depletion modulator. Mostly, the speed of those modulators is limited to on the order of 50 gigahertz because of the engineering of the RC time constant. But they are now currently in use in a lot of Silicon Photonics technologies, both embedded in a Maxinder Interferometer, so where you modulate the phase in one arm of the Maxinder Interferometer, and that gives you constructive or destructive interference, so you can switch your device on and off, or by embedding it in a ring resonator, where by modulating the signal on the ring, you're moving the resonant wavelength of the ring, and also you're going to switch your light on and off at a certain wavelength. The other kind of electrical function or electro-optic function that you definitely want in a lot of these circuits is photodetection. You want to be able to convert a modulated beam of light, an optical beam with a signal on it, to an electrical signal. And there the typical ways to do it is using photodiodes. That's by far the most efficient way to do it. You can also look at photoconductors or even photobolometers. But if you want to do a fast modulation, you typically need a photodiode. And for that you need like 3-5 semiconductors, but in the Silicon Photonics platform, the most common material used today is germanium. If you work at visible wavelengths, you can of course use silicon as well. Now, integrating germanium in the Silicon Photonics platform is a bit more tricky because you need to epitaxially grow your germanium inside or on top of your silicon, which is tricky. But again, luckily there, for that type of process, people have been paving the way for electronics as well, because already for like 20 years, almost strained silicon or germanium strained silicon is used for electronics. So the epitaxial growth techniques had already been developed a long way to integrate these detectors. Now, let me take you quickly through the fabrication process before we dive into like what is needed to design these circuits. And again, this is a typical silicon photonics process, but if you go to other material systems, you will encounter similar fabrication steps like epitaxial growth, lithography, and etching. And the fact that all of the photonic fabrication, photonic material systems use similar fabrication steps also means that they're suffering from similar problems in the design process. So if we start for a silicon photonics chip with a silicon layer of typically a few hundred nanometers on top of an oxide layer that optically separates it from a silicon substrate. So this is a material called silicon on insulator. It's typically bought off the shelf. Now the first step you do is then spinning a photosensitive material onto your wafer, in which you then project a pattern that you want to fabricate. In this case, we project a pattern of waveguides. That pattern is then, or the photoresist is then developed, and what remains is either the illuminated part or the non-illuminated part, but the pattern will remain in the photoresist. And now this remaining resist can be used as a protective layer for a reactive ion etching, which basically removes the silicon everywhere where there is no photoresist left. And then finally use a selective chemical rinse to strip the photoresist from the chip. And that gives you your waveguides. And okay, in the first instance you could say, job's done. But this is usually just the beginning of the fabrication process. Because in most photonic waveguide processes, there's not one layer that's being etched, but it's typically a few layers. So for instance, you can do shallow etching to make grating couplers or to make rip waveguides that you can use for modulators. Now, once the passive functions have been defined, you can now add active functionality, and that is typically done by implantation. So you implant P and N dopants, which can be used to make a junction for a modulator or a resistor that you could use for a heater. Now, once all these are been added, you basically clad the whole circuit with an oxide material, which you then planarize. So you basically have a flat surface for the next layer to be processed. Now, the one function that's still missing here is the detector. So if you want to now add germanium photodetector, you can selectively open up an area where you want a detector. You then epitaxially grow the germanium on top. You planarize it again with a polishing step. And then you're at a point where all the active functions are there and you can electrically contact things. And from this point on, especially in silicon photonics processes, you can reuse the typical metallization processes used in electronics. So, which means tungsten plugs to contact the devices and then copper metallization, typically multiple layers, and finalizing everything with an aluminum-based bond pads. So you now have a circuit or a chip which contains waveguides, modulators, detectors, and all the metallization steps. Now, this is a very simple PowerPoint flow. In reality, if you look at the process steps needed to build a chip like that, you run into hundreds of different process steps. And every process step, as we will discuss later, can basically have slight variations from wafer to wafer or even within a wafer. So that means that every circuit that you fabricate is going to be slightly different than every other circuit. I get a question here, can we please have the course materials? Yeah, I will make them available afterwards for download. No problem. Okay, so we have all the functions that we need here, except for the one elephant in the room, the laser. So how do you get the laser on such a photonic chip? Well, if you're working with 3-5 semiconductors as a platform, of course you have lasers already built in there. These materials are super for making lasers. On a silicon platform, it's a bit more difficult. So basically, if you want to introduce gain, optical gain for making light sources, you need semiconductors like 3-5 or germanium, or you need some rare earths like erbium or nonlinear processes. But the most common way to do electrically pumped lasers is still 3-5 semiconductors. So you need to integrate those on a silicon chip. And that is today is done with both bonding techniques and transfer printing techniques as by 3-5 epitaxy. But all of these techniques are still relatively immature compared to the rest of the technology flow. So again, why silicon photonics? Well, the scale, you can go to large scale manufacturing, you can go to submicron scale waveguides. And that actually gives you enormous benefits because you can now integrate many more functionalities onto the same footprint. This is an example of an arrayed waveguide grating. It's a kind of a spectrometer or filter circuit. This is done in a low contrast glass system. This is in medium contrast indium phosphide and in high contrast silicon photonics. And you see that from the glass to the silicon photonics, you get similar functionality in a footprint that is 10,000 times smaller. And this is important because the small footprint allows you to do something that you cannot do in these low contrast systems, and that is build really large circuits. So you can, similarly as in electronics, for photonics, if you go to high contrast material systems like silicon, you can start to call it very large scale integration. So you can basically get thousands or millions of photonic components on a chip. And we have seen this happening. So if you look at silicon photonics and 3-5 photonics, you see that silicon photonics, the integration density for silicon photonics chips is going much faster, it's increasing much faster than it is for any other technology. And that's just because you can now integrate these many components on a chip. However, there are still some questions, and there are now large-scale photonic circuits, but as I mentioned, everything is very sensitive. Does that mean that these large circuits actually work? And so it becomes tricky to really make use of these large-scale photonic integrated circuits technology. You need to be able to also reliably design these circuits, and you need to be able to predict that they're going to work. So photonic circuits give you this really interesting perspective now. Just like in electronic circuits, the functionality of a photonic circuit does not come from an individual building block. I mean, in electronics, it's not the single transistor that makes the function of the circuit. It's the concatenation and the connectivity of all these transistors that make the circuit work. And the same is true for photonic circuits. It's not about one modulator. It's not about a splitter. It's about how everything is connected. And just like in electronics, where transistors are not perfect, in photonics, these building blocks do not necessarily have to be perfect. You can actually build circuits to compensate for the imperfections of your photonic building blocks. So the strength of photonic circuits comes from the complexity that you can design. And this brings us actually to the main part of the course, is photonic circuit design. How do you actually go about designing a photonic circuit? So, like I mentioned, it's all about complexity, managing complexity of hooking up all these little devices together. Now, if you compare where we are with photonics today in terms of number of components and maturity of the technology and the capabilities of the design tools, we can compare ourselves to, let's say, fairly simple, like the 1970s or maybe the early 1980s of electronic circuitry. So if we want to scale this up, if we want to make really more complex things, the technology needs to improve, and that's ongoing, and it's steadily improving. But also the design methods need to improve. We need to be able to really translate our ideas into something that works, that we can first capture, translate the design idea to a circuit, simulate how it works, simulate how it should behave, check whether it can actually be fabricated, even in the presence of variability, in the presence of imperfections, and predict how well it's going to work, so that essentially if you want to make an application out of it, if you want to build a product out of it, you know what the yield is going to be, and therefore what the cost is going to be of your product. Now, like I mentioned, it's not because your circuits are complex that your building blocks are complex. We basically can live with a limited set of building blocks. We need a modulator, a detector, some waveguides, some couplers, etc. And we can build almost any circuit that we want. But the functionality comes from how you connect these together. And in order to design that functionality, you need to be able to accurately predict how it's going to work. So you need good models, you need good simulation tools. You need to be able to assess what the effect is of variability and non-idealities, and preferably also like parasitic light, what happens if light is not going exactly the way that you want it. Now, these are all very similar requirements that you need if you design electronic circuits. You can only design large-scale electronic circuits if the models of the individual transistors are good. If you can predict what the variability is gonna, how the variability is gonna affect your electronic circuits, and if you know the parasitics. So, given that we're talking with similar chip-based technologies and similar concepts of circuits, devices connected together with signal lines, we should be able to learn a lot from what has been done in electronic IC design. Because the world of electronic design automation, EDA, has been building tools that allow you now to make circuits with billions of transistors. Can we repurpose all that learning, or a lot of that learning, for photonics? And indeed, that's something, that's an evolution that started to happen, let's say, 15 years ago. And it started picking up pace in the last 6-7 years ago, is that design automation tools combining photonics and electronic design automation, mostly driven by the large companies that do design automation like Cadence, Synopsys, and Siemens or Mentor Graphics. They're trying to integrate these photonic design capabilities into their photonic design flow, into their electronic design flow. And that's not that easy, because even though a lot of the concepts are the same, and a lot of the design process is the same, there's a substantial set of differences. I see a raised hand by Amir.
This is a really great presentation. I'm really enjoying it. Thank you so much. But a quick question, actually. I think what difference here is that, like, intrinsically, a lot of these VLSI system with many transistors or digital devices which are more tolerant naturally to, like, sort of variations. And I would say 99% of, I assume, like, photonic integrated circuits are analog devices.
Exactly.
Which I think they're more susceptible to this. I don't know how people solve this in analog electronic. I think, I'm no expert, but I think there is also, they, didn't went as far as digital electronic in terms of repeatability. And
no, that's exactly true. I mean, indeed, you don't find analog electronic circuits with billions of transistors. These are typically much smaller in scale than the digital systems. That's true. And they're much more sensitive than digital signals. So you can, in a way, indeed compare these analog circuits today, or analog circuit design, to photonic design in some ways. But it is true that, at least until recently, analog circuitry was still an order, 2 orders of magnitude less sensitive to fabrication variations than photonics. It's only when people started to try and do analog design in, let's say, 28 nanometer nodes or even more aggressive nodes, which is very, very difficult, that this problem with variability really started to emerge. And it turns out that a lot of the concepts that are now being developed to address this problem in analog electronics can actually also be applied to photonics. So what I meant to say here is that we do see these process flows emerging, where people take all the concepts from electronic design and try to apply them to photonics. And in some cases that works, it's a one-to-one translation. In some cases it doesn't. So what we're seeing now is that, well, we now see for most fabrication processes that are out there, there are already initial PDKs, process design kits, which contain libraries with building blocks, with basic models that allow you to do some predictive design for your photonic circuits. But it's still at a much more rudimentary stage than you find with electronic design. Now that brings me to the point of design flow. I mean, can we use the same design flow as in electronics? And just to set the semantics right, what do we mean with a design flow? Well, a flow is essentially like a pattern of activities, typically going in one way from left to right, multiple tasks, and every task has an outcome that feeds into the next task. And for design, well, that's basically the idea or the process in which you convert an idea into something real. So the purpose of a photonic design flow is very simple. It's to take your idea for an application and translate it into a chip. And not just any chip, it needs to be a chip that works. I mean, that's often something that is a bit overlooked, especially in research, is that people design a chip, but they don't simulate it, so they're not even going to know if it works. And in many cases, people design lots of chips, but not a lot of them work. So if you want to apply this to product development, this is not something that you can afford. So the design process needs to maximize the chance that your chip will work. And all the steps that you take should help you move in that direction. So what's a typical design cycle or a design flow looks like and is actually very much based on the design cycle that we use in electronics, is the first step is to take your idea and translate that idea, the function that you want to achieve, into a circuit representation. So that's the most creative part of the design process. You need to take the idea and then figure out how you can build a circuit that basically transforms your input signals to your output signals exactly as you want. And an input signal could be something that you want to sense, or it could be a digital communication system signal. But in the end, you have a system that converts a certain type of signal into another type of signal, input and output. And you have to construct a circuit that takes these input signals and converts them into output signals. And this is still at a very abstract level. I mean, you draw a circuit based on little rectangles and building blocks. The next step comes to translating that circuit or that abstract circuit into a physical implementation that can actually be fabricated. So the first part we call the front-end design, the second part we call the back-end design. And that physical representation is typically a mask layout that can be used by semiconductor processes to fabricate your chip. Now, essentially, okay, if you end up with a design that needs to be fabricated, you're done, right? Well, not quite, because you cannot fully decouple the design cycle from the actual fabrication process. So you need to be aware of the fabrication process, and at the end, your chip is going to come back, and you need to test it. And so you need to take that testing and the requirements for testing already into account during your design process. So I typically consider the fabrication process and the test actually as essential to your entire design cycle. Now, if we look in a bit more detail into the front end, there's two main activities that we see there. One is the translation of your idea into circuit blocks, into circuit diagram. The second is simulating whether that circuit actually does what it needs to do. And that's obviously an iterative process. In the back end, there's three major steps that you can identify. First of all is translate that circuit diagram into a layout, which means patterns that can be fabricated. Well, once you have your patterns, you need to verify whether they actually meet the design or the fabrication rules. For instance, you shouldn't draw lines that are too narrow to fabricate. The second verification step that you also need to do is to check whether your fabricated layout actually corresponds to the original circuit that you designed. And so that means that you need to make the translation back from a layout to a functional description and basically compare the two functional descriptions and maybe their behavior and their simulation to know whether it performs as it should. So let's go through each of these steps in a little bit more detail. Well, first of all, let's start with the idea. I mean, an idea is kind of an abstract thing, so the first thing that you need to do is structure that idea into something that you can then use to build a circuit from. So what should your device do? And typically you break that down into what are the signals that go in and what are the signals that go out? And what is the operational principle in between that should transform these signals? You also need to devise some specifications, of course. How well should it work? I mean, do I expect noise? What should be my signal to noise ratio? What will be the circumstances in which it will be used? Will it be an automotive where I have a temperature budget of -40 to 120 degrees C? Or is it in a well-controlled thermal environment that I don't have to worry about temperature? So a lot of these things need to be thought of in advance, because otherwise you might design something completely different and something that doesn't work in the setting that you want it to. So when you have the specifications and especially the idea of what the signals go in and out, you go to the next stage. And that's your front-end design, your design capture. Now, the way you capture a design is, again, you start more or less from your behavior that you want. So signals in, signals out, the flow of information that is going on in your circuit. And the way you represent that is typically with a schematic, where you start with a library of building blocks that you put together and you connect together with wires, in this case waveguides, describing how the signals should flow between these building blocks. And this is a concept that's also used in electronics, making a schematic. And it's the most difficult part of the design, actually, because building a schematic is a very creative process. There's no recipe that I can give you now that basically translates whatever function you have in mind into a schematic. That's the creative part, the inventive part, the innovative part of the circuit design, or at least the most innovative part. Now, building a schematic is typically done in a schematic editor, and this is just a mock-up because I don't want to show any specific tool sets here. But if you look at the different vendors of software for making photonic and electronic design, you will find an editor that looks a bit like this. So where you have a component library with building blocks that you can use, you can hook them together on a canvas, you can draw waveguides or signal lines in between them. You can set the parameters of each component, so many of these components are parametric. You usually also have some command prompt or scripting interface that you can use so to automate certain tasks. And you have an interface to circuit simulation, so that once you've built your device, you can actually also simulate its behavior. Now, this looks okay if you combine like 5, 10, 20 blocks on a canvas. But if you start thinking about a circuit of hundreds of building blocks, this method typically breaks down. So it's important when you build a circuit, when you put circuits together, to think carefully about hierarchy. You basically split your circuit up into sub-circuits that can be reused and that basically reduce the complexity of every layer in your design. So for instance, if I want to make a filter circuit that consists of a coupler and 2 delays, but then in one of these delay lines I want a ring resonator, I'm going to separate that delay line into 2 waveguides, a ring resonator, and the ring resonator itself could again be another circuit that consists of a coupler and a waveguide. So that way I can design every part independently, also make it parametric, and then reuse those sub-circuits as building blocks in the higher level. This again takes quite a bit of thinking and structured work to make sure that you partition your circuits accordingly. Because if you run into like single layer circuit or monolithic circuits that consist of thousands of building blocks, it's very easy to slip in an error and you're never going to find it. Now there's an interesting thing here, because we see that these circuits are connected with wires. But what is a wire? I mean, in electronics, at least as long as you don't go to RF design or microwave design, a wire is just an electrical line, and you more or less assume that it's instantaneous. The only function the wire has is to make a galvanic connection between 2 building blocks. But as I mentioned earlier, waveguides are a bit more tricky, because a waveguide has a certain phase delay. It also has a certain time delay if you propagate a signal through it. So you can treat waveguides in different ways in a photonic circuit. And this is a very conscious choice that you have to make. On one hand, a waveguide can be just a wire. The only function that you care about is that the signal goes from one point on the chip to another point on the chip. You don't care too much about the delay. It's going to be fast enough anyway. You don't care about how much phase delay there is, so that whether the waveguides, the wave arrives in phase or out of phase. You don't care. It just needs to connect point A to point B. And in that case, your waveguide is just a link. It's the equivalent of an electronic wire. But a waveguide can also perform a real function, in the sense that it provides a specific phase or time delay that you want for your functionality. And the key functionality where this typically occurs is a wavelength filter. Like I mentioned earlier, a Maxinder Interferometer consists of two waveguides with different path lengths. And by controlling the path length, you control which wavelengths interfere constructively or destructively. So in that case, you want very, very good control over what your waveguide does. In that case, it's therefore much more prudent to treat the waveguide as a building block. So where you can fully specify in that building block what its parameters should be, what should its length be, what should the type of waveguide be that is used. Is it a rip waveguide or a strip waveguide or any other type of cross-section? And in that case, of course, you need to connect these building blocks together with just a pure logical connection, because eventually, if you want to put this on a chip, you want that the splitter and that waveguide is connected really directly, and there's not an intermediate piece of wire in between, because that would essentially ruin its function. So this is one of the key things to think about if you do photonic circuit design, and that is, what is the role of my waveguides in each part of my circuit? Is it a wavelength dependent or interferometric structure? Then I probably need to treat it as a building block. Is it just a wire that connects two parts together and I don't care about the actual delay? It's not part of some larger interferometer. Okay, then you use just a wire, and that simplifies, of course, your description of your circuit. And it's important that you do this at the level of the schematic, because that will provide instructions for the person who does the layout, whether it's yourself or someone else. The translation into the layout should take these things into account. Okay, once you have your schematic, the next part is figuring out whether it works. So you need to simulate it. And of course, that's going to be in an iterative way. It's going to be rarely the case that your first attempt is going to give you exactly the simulation results that you want. So you're basically going back and forth between your schematic and your simulation. Now, here photonic circuit simulation is slightly different than electronic circuit simulation. First of all, we're talking about circuit simulation. So whatever method you use, you should be able to put a fairly large circuit in it and do it efficiently. That means that the traditional photonic simulation methods that people use, like FDTD, are totally out of the question. You basically need something that's based on equations or based on data, that has behavioral models that mimic the physics inside each component, but without going into full electromagnetic simulation. Now, the big problem with photonic circuit simulation is that at this point, there's no standards. Every design tool has its own circuit simulation for photonics, which means that there's no standard way to describe the models of the building blocks. There's no standard way to represent signals in a photonic circuit simulator, which means that it's actually for the people who have to develop these models and to have to provide you with building blocks, that's a fairly high threshold for developing new models, because you have to do it for every individual tool independently. And as a result, what we have at the moment is actually a very fragmented landscape and a lot of design libraries that do not yet contain good models. So that's a bit of a problem if you want to do larger scale circuits. And it is a sign of the fact that photonic design landscape is still fairly immature compared to electronics, where essentially everything can be simulated with SPICE or Verilog A. Now, talking about circuit models, what should a circuit model actually do? Well, the only requirement that you actually have is that it's accurate, in the sense that if you send in an input signal, what comes out is an output signal that represents what the circuit is doing. That represents the real behavior. You don't really care what's internally happening in that circuit model as long as the signal in to out does what it has to do. And preferably you want to be able to do that in frequency domain, so to, for instance, design a wavelength filter, and in the time domain, for instance, to design a communication system. Preferably it's also fast, because you want to cascade lots of these blocks and you don't want to wait a day every time you make a change to your circuit. So you should be able to run circuit simulations in a matter of seconds or minutes, not hours or days. Typically also, if you have building blocks that are parametric, your circuit model should also have meaningful parameters. And preferably, after you fabricated it, you should be able to perform a measurement on that block and basically check whether it matches the simulation, and maybe even update the parameters. Now we see two main types of circuit blocks or circuit models today. You could call them white box and black box models. In the white box model, typically tries to capture the physics of what is going on in there. So typically it's a set of equations that they're approximate equations, but still they're a set of equations that try to mimic the physics of what is going on inside the circuit block. A black box model is just a mathematical construct. It basically can be based on fitting of measurements or fitting of electromagnetic simulations. You don't really know what is going on inside there. You could use machine learning, you could use all kinds of advanced fitting methods, but the only important part is that if you send a signal in, what comes out is still meaningful. It's still a good signal. So it doesn't really matter how you do it. As long as you have these models, you can simulate your circuits. Now, a common way of describing circuit models is using scatter matrix or scatter parameters. This is a method that works very well for all passive building blocks, like waveguides, splitters, filters, all the building blocks that essentially just move waves around internally, but do not perform active functionality like modulation detection or nonlinear effects. And the attractive thing is that these scatter matrices allow you to describe your passive circuit in the frequency domain in a very elegant way. You basically have all the couplings between all the ports just as function of frequency, and that fully describes the behavior of that passive building block or that passive circuit. And that is very useful for making wavelength filters. For instance, arrayed waveguide gratings, ring resonators, Maxinder interferometers, they're all passive circuits. And typically you want to design these circuits to have a certain frequency response, a certain wavelength response. So the nice thing about these frequency domain simulations is that they're also typically a lot more efficient. So you can do it much faster than you do it with time domain simulations, which you have to redo for every possible input and output signal. Now, these scatter matrices basically give you a very clear way of how every input wave is coupled to every output wave, and I should say every input port coupled to every output port. You just have to be very wary about what you mean with a port. Let's say that you have a splitter component here, which has 3 waveguides, one input, 2 output waveguides. But if every waveguide supports 2 guided modes, for instance, a TM polarized mode and a TE polarized mode, that means that this is a 6-port device. Because every orthogonal mode that can be used to excite a circuit, it should be considered as a port. So that means that if you want to describe this component and you want to make use of all the modes, you have to have a 6x6 matrix that describes the coupling between every set of ports. If for some reason you decide that you only want to use your circuit for TE polarization, then you can describe it as a 3x3 matrix, but you also have to incorporate all the coupling that goes from TE to TM is then incorporated as a loss inside inside the circuit or inside the device. Now, this makes frequency domain simulations quite convenient. You can simulate a lot of functionality just with frequency domain, but the moment you have active functionality like modulators and detectors, or nonlinear elements, you'll also need time domain simulation. And so that basically means that if you want to simulate a circuit in a time domain, you now have to define how you're going to excite your circuit, what is the input signals that you're going to send into your circuit, and where are you going to monitor the outputs. So with a time domain simulation, you always have a stimulus and a monitor that you need to run. Again, this makes use of behavioral models. So you're not doing full electromagnetic simulation, so it should be much faster than running FDTD, and it should support large circuits, but it's typically much slower than a circuit simulation, and it only gives you the response to one specific stimulus. So if you want to send in another signal, you have to redo that simulation with another signal. Now, in a time domain simulation, what you have is that you basically connect building blocks together, and then your signals propagate from one building block to the next, and then inside the building block there is a little piece of code or a scatter matrix or a model that describes how the input signals are coupled to the output signals. Now note that the signal here in photonics is something slightly different than a signal in electronics. In electronics, the signals are described by voltages and currents at specific points in your circuit. In photonics, we're talking about waves. And we're talking typically about waves modulated on a carrier frequency. So instead of just seeing the photonic wave as the actual electromagnetic oscillation, which would require femtosecond time steps in your circuit simulator to model, we usually describe a photonic signal as an amplitude and phase modulated onto a carrier wavelength. So we only describe the complex envelope. And that way, you may take much larger time steps. You basically just need to take in the time steps that of the parts in the circuit, or of the fastest element in the circuit. So if you're using gigahertz signals, you need, let's say, nanosecond or 100 picosecond scale time steps. If you have megahertz signals, you only need 100 nanosecond scale time steps. So by using a complex envelope, you can save a lot of time in your circuit simulations. Now the only problem is, with the signal, you're not there yet. You have an amplitude and a phase, so that's essentially two numbers, but in many photonic systems there's much more going on inside your signals, inside your waveguide line. So on one hand, a wave can propagate in two directions. So you have a forward propagating wave and a backward propagating wave, and these essentially are not coupled. So that's, instead of having just amplitude and phase, you now have amplitude and phase in two directions in your waveguide. On top of that, well, the amplitude and phase give you two numbers as well, but then you could use wavelength division multiplexing. So you could have, within a single waveguide, you could have multiple wavelength channels, or you could even have a full spectrum. For instance, if you want to build a spectrometer. And then I already mentioned, inside the waveguide you can have multiple guided modes, a TE mode, a TM mode, and even higher order modes. And each of these modes or polarizations also need to be represented by a different number. So you quickly go into a situation where you have 2 times 2 times n wavelength channels times m waveguide modes numbers at every time step to build to represent your photonic circuit. And this number depends on your application. For instance, if I want to make a very simple case, I want to simulate a single waveguide, a single wavelength optical link. It's only propagating from the source to the detector in one direction. We only use one wavelength. We only use on-off modulation, and we only use one waveguide mode. Well, okay, in principle, you can describe your optical signal with one number. You don't even need your phase. However, the moment you go, for instance, to a WDM bidirectional link, which has to go in two directions, where you use coherent modulation, for instance, where you so need amplitude and phase, and you have 32 wavelength channels, still in one mode, yeah, now you have 128 numbers. So at every single time step in your circuit simulation, in every single waveguide, you need 128 numbers. And it doesn't stop there. If you go to dense WDM with like hundreds of wavelength channels, and you want to correctly assess all the crosstalk and stuff like that, yes, you need all of that, and you also use mode multiplexing. You go into the thousands of numbers for every time step. And if you want to make a spectrometer where you want to capture the full spectrum, let's say for instance with a 5 picometer resolution, yeah, then you're talking about on the order of 100,000 numbers. So this can quickly become intractable. And like I said earlier, there's at this point no real standard to represent all these signals. Every circuit simulator has their strengths and weaknesses and can either accommodate some of these or all of these or none of these. And there's no standard way to build your models to handle all this. So photonics circuit design at this point is still a bit at a loss, where you can design your circuit, but to accurately simulate it depends very much on the tool you use and the application you want to simulate. At this point, this is not a clear-cut. There's no clear-cut solution. Well, some people try to do photonic circuit simulators, simulations in an electronic circuit simulation tool, like SPICE. And actually, you could argue that it's possible, because while electrical signals are described by voltage and current, and you can apply that kind of formalism to other fields, in principle you could apply it to photonics by saying that your voltage corresponds to your electrical field component in your waveguide and your current to your magnetic field component, but it's still a very non-intuitive artificial construction. So actually what we see is that people try to co-simulate photonic and electronic, but it's always a bit tricky. So let's take this example, for instance. Let's say that we have an electrical circuit. It's a very simple one. It's just an optical link with a transmitter, a receiver, and a waveguide in between. And so you could look at your electrical parts of your circuit. So your signals are going in, and then you have an optical part of your circuit in between. So some components between electrical and optical do overlap. So that's again a bit of a problem. So how can you co-simulate that? How can you simulate this entire system? Well, there's different approaches, and none of them are perfect at the moment, but people are working on it. You could, for instance, just say, I'm going to do everything inside my electronic circuit simulator. So I'm trying to build my photonics as, for instance, very log A models, or even a SPICE representation of my photonic circuit. I'm going to mimic its behavior, signals in and signals out, as very log A models. Now, actually, this works, but it's typically limited to the use cases where your signals are only described by a few numbers, like a single wavelength case, or maybe a few wavelengths, but a very small number of data, or a very small number of quantities inside each signal. And indeed, the typical use case for these very log A models is communication systems, or very simple communication links. Now, okay, if it doesn't scale up well to more complex systems, what if I would put the electronics in a photonic circuit simulator? The photonic circuit simulator might handle these more complex cases, and electronics, I mean, they're just models, so I can basically write my electronics as photonic models, and I can simulate my electronics as well. Well, again, there's tools that do this, but the catch is here that, I mean, we're now trying to put an electronic circuit simulators, which is orders of magnitude more mature than photonic circuit simulators, and we want to put that in a photonic circuit simulator. How many electronic designers are you going to convince to go with this workflow? They basically have to abandon their trusted tools, which are in many cases much more mature than the photonic tools, and they have to abandon their trusted design kits that have been supplied by the fabs. It's not going to happen. It's good for some experimental work, but not as a solid design flow. So if you want to make both work, well, there's not much that you can do except basically simulating the electronics into an electronic simulator, which is trusted, which you know is going to work, and simulating the photonics in a photonic simulator. And okay, in a case like this, you have a one-directional flow of information. Your current driving your laser is basically handed over to your photonic simulator as a waveform. Then you run your photonic simulation, and then the current coming out of the photodetector is then sent into the receiver. So as in a one-directional flow of information, you can just run sequentially these three simulations. However, the moment you have feedback loops that basically go back and forth between your photonics and your electronics, it becomes a bit more complicated. And in that case, you need to move to a situation or to an implementation that takes a photonic simulator, an electronic simulator, and hooks them together and operates both of them in lockstep. Now, this is essentially mixed signal simulation. It's a technique that's already in use for combining digital and analog electronic simulations. So today we are seeing some implementations that are already in use. One example, for instance, is the combination of cadence with numerical, where you have this mixed signal co-simulation between, on one hand, an electronic simulator for the electronics and a photonic simulator for the photonics, with continuous exchange of signals and information between the two. Now, this was a big chunk on simulation, and I basically told you that there's a lot more boundary conditions and limitations today as actually the thing that you can do. But okay, circuit simulation does work. It's just at this point, it's still relatively limited, and most importantly, it's not standardized, which gives us actually at this point a very limited set of models and a very low maturity in the circuit models that you can use in your design. Now, with that, I want to wrap up the front-end design and move to the next stage, which is the back-end design. How do we now translate our circuit which we built into a physical implementation? And for a chip, the physical implementation means mask layers that can be used for each pattern layer that we need to fabricate. So for each lithography step in the fabrication process. So that means geometric patterns. Essentially, a translation of a circuit to a fabrication ready form is nothing more than a drawing. You typically have polygons organized on different layers with also additional layers for annotation. For instance, with marks that help you verify whether the drawing is correct. Now, again, drawing all these polygons in their raw form is typically not done. We use the same technique as we use on the schematic. We basically break up our layout into reusable cells that can be placed and transformed and reused throughout the layout to reduce the complexity. Again, not having one flat layout with billions of polygons, but having a hierarchical structure that can be reused. And then basically all these building blocks can be connected with wires or with waveguides. Now, that is done in a similar design environment as we have for the schematic. Again, if you go to the different design automation frameworks, they all provide you with some form or another of an interface like this, where you again have a canvas of building blocks, a palette of building blocks. You can drag and drop on a canvas, you can draw on a canvas, you can play with parameters of certain parametric building blocks, and you can even script. So again, similar type of functionality. Now, at the core of this is what we call design cells. So what you find in your palette of building blocks is design cells which contain different representations. So typically a layout, what are the polygons, or what are the other cells that I'm going to place inside these cells. But they also contain links to the more the schematic part, like the symbol and the models that you can use. Now, you have static cells. A design cell can be static. It can just contain data. And there's actually standard file formats to implement this. There's GDS2 for layouts. There's EDIF, which is basically a design and interchange format for all these different aspects. But in reality, we find that most of the cells that are being used are not static cells, but are parametric cells. So essentially, a parametric cell is no longer just a set of data, it's a piece of code. It basically takes a set of parameters from the user, like for instance the radius of a ring resonator, and then the code inside is evaluated and it spits out the resulting data, the layout of that ring resonator with a certain radius. Now the problem with such an evaluator is that this is tool vendor dependent. It's a piece of code. It's not static data, and there's no standard to really write these evaluators. These are very, very, very tool dependent. Now, if we look at this layout, what is in such a layout? Well, it's essentially just polygons, like I mentioned. So you basically have a set of polygons on certain layers. So you typically, if you draw a photodetector, you would have a layout that you have a set of polygons that describe the shape of the waveguide, how the waveguide couples into the photodetector, and then the shape of where the implantations need to come, and the shape where the germanium needs to be grown, and the place where it needs to be contacted electrically. And all of these are shapes on different layers. Now, we see that there's a lot of correspondences between the schematic and the layout. Both are hierarchical, use hierarchy, and both use cells to represent the building blocks. So it's logical that there are tools that help you translate your design function, which you defined as a schematic, into a layout. And that is what we call a schematic-driven layout. Essentially, you take your schematic and you translate every building block in the schematic to a corresponding building block in your layout. And then either you can automatically place all the building blocks that they fit together, or provide some guidelines like fly line drawings for the user that helps you connect that helps you connect all these blocks together. And this is essentially becoming a place and route problem. So we're not, in this case, in circuit design, we're not in the business of drawing individual polygons. No, in circuit design, we try to take as much as possible reusable building blocks, which we then hook together. So the polygons that we're drawing are usually only the connection waveguides, while everything else is just a matter of placement. Of course, with routing waveguides, it's similar as routing electrical wires in electronics, except that there's some more boundary conditions. When you're routing waveguides, you typically have to take into account that a waveguide has a certain minimal bend radius. So you have to make sure to have sufficient space to round the waveguide. You also have to make sure that waveguides do not come too close together, so that they don't get crosstalk, that you don't get a directional coupler essentially. And maybe the biggest constraint is that most photonic platforms only have a single layer of waveguides at your disposal. So that basically means that you have to be very careful for waveguides not to cross, how you're going to route them. While for metal routing in electronics, you typically have multiple layers of metal. So you can easily make crossings, or you can jump to another level. In photonics, that's actually a quite complicated process if you have to introduce crossings. Now, schematic-driven layout tools are actually helping you with this. So they provide you with visual cues, with already partial auto placement of your devices. And we see them now emerging, in many cases based on electronic schematic-driven layout tools. They really help you like visually draw all the components on your chip. Now, once you have your layout, the next question is, can I actually fabricate this layout? Is this compatible with the fabrication process? And this is a step we call design rule checking. Typical problems that you encounter during design rule checking is whether some features that are too small, like two components too close together, or a sharp angle somewhere because two waveguides come too close together and their trenches intersect. Minimum line with minimal spacing. And also some layers that are not supposed to be on top of one another, or that are required to be on top of one another, but they're not. So that's the type of error you have, and of course you need to iteratively fix the problems. However, there's a little catch. The tools that are used for photonic design rule checking are actually the same tools as used for electronic design rule checking. Except, of course, that in photonics we have all these curvy, linear, nice curvy waveguides, while in electronics most patterns, most designs are based on rectangular designs along Manhattan directions. So there's still a lot of innovation to be done on these design rule checking tools to really get the most out of them for this kind of omnidirectional polygons that you find in photonics, to avoid that they give too much false errors, or to avoid that they miss certain errors or certain gaps, for instance, that you are not caught. So this is a kind of a critical thing. If you find design errors, it's difficult for these tools, at least at this point still for photonics, to identify for these tools what is intentional or what is essentially an error. Now, one step that also becomes important in this stage is the problem of pattern density. In most semiconductor processes, every layer tries to maintain a certain uniform pattern density, because that determines what the edge chemistry is going to look like on a wafer scale, or what the polishing rate is for your chemical mechanical polishing. So that means that if you make a photonic design, you need, at some final step, some additional tiling is being added in the areas which you're not using, that controls the pattern density. Now, in general, that works well, except, of course, in some cases you have photonic devices or photonic circuits that consist of large areas where there's no room for tiles. For instance, an arrayed waveguide grating typically has this large area of unpatterned slab, which is basically the free diffraction, free propagation region, where of course you cannot put any tiles. And you have to be careful with designs that include such features, that you do not completely wreck the required pattern density of your fabrication process. And depending on the foundry, they might still allow you to go through with it on your own risk, but they might also just basically forbid your design for going into the fab, because the chance of success are going to be slow anyway. So obviously this design rule checking is an iterative process. There's always going back and forth between layout and rule checking. And on top of that, there's a second verification process that's needed. That you need to check whether your layout actually corresponds to your original design intent. And this is called schematic versus layout. It's kind of functional verification. Now, what happened? What is that actually? Well, in electronics, it typically means that when looking at there's an automated tool that looks at the layout, basically identifies a component and looks if they're properly connected, which means there's a wire connecting the components together. Now, in photonics, a connection is slightly different from an electronic connection. While in electronic it's sufficient that two wires physically touch, in photonics you also need to look at the direction of the waveguide. So if you make a sharp angle in a waveguide, you're going to lose a lot of light. But you also have situations where two waveguides are can actually cross if you put an engineered crossing in between. So these special cases for photonics you need to be able to pick them out. So connectivity checks are slightly different in photonics than in electronics, but now we already see that quite a lot of tools offer this kind of connectivity check. A much more difficult part of the verification is to check whether all elements in your circuit will actually perform the desired functionality. Okay, there's simple cases, like if you have a splitter in your schematic, you might identify that indeed you have a splitter in your layout, and you can check that off as the right function is in place. However, a lot of functionality is implemented in the form of waveguides. And with the waveguide, the function is fully determined by its optical length. And the optical length is determined by the physical length, okay, which you can measure on the layout, but also by its propagation constant. And the propagation constant depends on the geometry, the width of the waveguide, the thickness of the waveguide. So if you now have a waveguide there, which forms a certain shape, what is the actual width of the waveguide? Well, in the straight sections, that's clear. But in the bend sections, you have now discretized a nice smooth bend with a polygon. And so depending on how the discretization was done, you might actually end up with a slightly different width on average for your waveguide, resulting in a slightly different optical length. And that might translate in a different functionality. So it's not that type of verification is much more difficult to do, because you now have to really look at what is the intended function of this component, and is the geometry that's being laid out actually corresponding to that intended function. Of course, again, this is iterative. You might have to redo your layout. You might have, in some cases, even go back to your schematic to fix your schematic, because certain things might, for instance, not possible. But in the end, what you do in this verification step, you want to extract from your layout, again, that functional description that allows you to do, after your layout, simulate the behavior of your circuit with the actual waveguide lengths that are in there, with the actual crossings that have been introduced to basically allow you to connect everything, which, for instance, in this case, gives you additional crosstalk between and additional losses in different communication channels. So, like for instance, with and without, the left is before, right is after the schematic versus or after the layout. So before is the ideal situation, but after you see that there's crosstalk because of the crossing that we had to introduce in the layout. Okay, let's say you have your layout. Next step, fabrication. Let's send it off to the fab. And typically, as I showed you the process earlier, you have multiple layers, so there's a lot of process steps, typically a few hundred process steps consisting of layer depositions, lithography, etching, polishing, annealing, implantations, etc. Each of these steps is not perfect. So just to give you one major example of things that are not perfect is lithography. Lithography is essentially an imaging system, which means it acts as a spatial low-pass filter. So if you draw something like there at the top with perfectly rectangular corners, you're going to end up with something that's rounded at the bottom. You can compensate for that, and there's some techniques that you can do prior to fabrication is add these computer-generated serifs or features to it that might help you correct some of that errors, but it's not always possible. And we're going to cover the problems of variability in a few minutes as well. Now, so that means that you have to go back to your layout, and again, maybe in some cases you have to go back to your design functionality. Now, one thing that helps you a lot in that fabrication is the fact that you have what we call a PDK. This whole circuit process actually is built on top of a concept of a process design kit, which is essentially the interface between a fab who has developed the fabrication process, who has actually tested and built a library of building blocks, who knows the fabrication rules, and the designer who has to take these components, put them together, and make a working circuit. And in between, the handoff of that information is called a process design kit. And that contains like lots of information, for instance, inline process data from wafers, for collected statistics from how does the waveguide gap or the waveguide width vary over time or vary between devices. It contains information about the fabrication process, and in many cases you can imagine what can be extracted or what can affect the behavior of your circuit. And there's lots of things in that fabrication process that can affect the behavior of your circuit. Just to give an example, I mean, and this is just for a few parts of the process. Just in lithography, you have problems with your mask, you can have variation on your lithography tool, and you can have variation in the resist and variation in the wafer. And then you just did the lithography step. And after that, you need to go etching, where you have etch chemistry that can vary over your wafer. You have to do polishing, where you have slurry that can vary over your wafer. So eventually you have a whole set of process conditions that can change from die to die, from wafer to wafer, from lot to lot, which will affect obviously your device geometry, And as we know, in silicon photonics especially, changes in device geometry have a very strong effect on changes in the optical device properties. So any variation here translates in variation in your devices, which obviously affects your circuits. But in the end, if you want to have a system, you want to know whether your system has to work. So you basically need to be able to predict what's going on here. How will it affect my system? How will it affect the input to the output signals of my system? And we can find that variation at various levels. So you have variation on a die scale, you have variations on wafer scale, and you have variations on wafer to wafer and lot to lot. Now, to give you some ideas how all these levels are mapped together and how that affects the behavior of the photonics, let's just look at a very simple waveguide. I mean, waveguide, let's describe it by two simple parameters, the width and the thickness of the waveguide. And there's more because there's a sidewall angle as well. Now, if we look at the width and the thickness, and this is just in simulation, and for that we simulate the group index and the effective index, so essentially the phase velocity and the group velocity, then we see that that width and thickness is nicely mapped onto group velocity and phase velocity. Now, if you now have this map, and you know how, for instance, your width of your waveguide, your line width of your waveguide changes over the wafer, and for instance, this is a map of line width over a wafer, you see that the line width varies with like 20 nanometers from the edge to the center of the wafer. That's quite a lot of variation. We were complaining about the 1 nanometer variation earlier. Here we're talking about 20 nanometer variation over a wafer. You can imagine how much that will affect your effective index and your group index of your waveguide, and as a result, how much that will affect your circuit. Now, how can you actually quantitatively predict this? Well, for that, you need simulations. So in the normal design flow, we basically take components from a PDK, we put a circuit together, the netlist, we make the netlist, the layout, and we run the simulation, and we get the behavior of the circuit as function of the components that we used, as function of wavelength, for instance. Now, if we want to now assess what is going on in the presence of variability, we need some additional information. First of all, we need to know how sensitive each of these building blocks is to, for instance, a variation in line width or a variation in thickness on the wafer. The second thing we need to know is how is the line width or thickness or any other fabrication parameter roughly distributed over the wafer. So we basically need wafer maps or a model of a wafer map. Now, once we have these three things, we have our circuit, we have our sensitivity, and we have a map of fabrication parameters, we can now combine these into a set of Monte Carlo simulations. So we basically project our circuit onto these wafer maps. Then for each element in the circuit, we calculate how its performance parameter is changed as function of the local line width or thickness or implant conditions. And then we run the circuit simulation. And we just move the circuit around over the wafer. So we have all the different types of conditions. And now we get like a whole cloud of transmission characteristics, which we can individually analyze based on some metrics like crosstalk or correct wavelength. And we can do yield prediction. And this can help us build a better circuit. Just to give a very simple idea of how this can help us construct a circuit and make it better, let's say we want to make a 4-channel drop filter. So we have light coming in the circuit here, and basically every ring resonator drops a different wavelength of light. And we designed everything to be nicely spaced with 1.6 nanometer spacing, or 200 gigahertz. However, if we now run this through our wafer scale Monte Carlo simulator, we find that the transmission is all over the place, and the spacing between the channels in the same circuit is also all over the place. It's definitely no longer 1.6 nanometers, it's going from 0.6 to 2.6. That's really bad. Now, it turns out that because most of these variations are acting on a somewhat longer length scale, you can just do some simple changes in your layout, for instance, bring everything closer together, and now we still see that the circuits over the wafer do vary a lot in terms of absolute wavelength, But because the rings inside each circuit are much closer together, they see much more common variation, and the line width or the wavelength spacing between the rings is much better. And this is something that is very difficult to assess without such a tool. Okay. The last step, of course, is testing. If you want to know whether your circuit is working, you need to know how you're going to test it, and you need to do that at the design stage, because you have to put the test structures or the test inputs and outputs also on your circuit design. Now, of course, that would automatically feed back into your design, so you need to take both of them into account at the same time. So, how do you typically test? Well, there's many ways to do testing. Sometimes you need to fully package your circuit, but preferably the earlier you can test, preferably at wafer scale, the better. Now, that's one of advantage of Silicon Photonics, is that you have these vertical grating couplers that allow you to do this efficient testing. But it depends very much on the application. It is a challenge, though, to define good tests. Basically, you have to identify what are the representative parts of your circuit. Can you isolate them? Can you make sub-circuits to test individually? You have to know what quantities you want to get out. And just to give you an idea, for instance, even testing for the most simple device, which is a waveguide, is already hard, because the effective index, the key parameter of a waveguide, is a phase-dependent parameter, and typically measuring phase in optics is quite hard. It's much easier to measure intensity. So measuring effective index is already a tricky question, let alone all these other components that you want to test. Okay, I'm not going to go deeper into that. We started out with this design flow, which looks very simple. In reality, it looks a bit more like that. So it's not that straightforward. There's a lot of interaction, there's a lot of going back and forth. So obviously, this is also something that your design tool needs to support. I mean, that you can easily exchange data between these individual steps and modify your design. Go back 5 steps in your design flow, modify something, and it nicely propagates back to where you were originally. So the exchange of information in this type of system is important. That can be through files. That's the most primitive way, like saving your files as GDS, but also for netlists and schematics. But more likely, this is either done in databases, which in many cases are proprietary, although there's something like open access as a standard database format. Or you can also embed information in code. And this brings me actually to a very important distinction. There's 2 big trends in photonic design. One is designing in code, one is designing in a GUI, point and click. Now, for most people, designing in a GUI has a much lower entry point. People are familiar with Windows or similar system like point, click, using your mouse, drawing, dragging and dropping, etc. However, designing in code has a lot of benefits that eventually pay off. Just to give you some pros and cons of these 2 different design paradigms. I mean, if you use code, you can basically use all the techniques that are already developed and the tools that are developed for software development, like version control, like debugging, like automated build tools, documentation tools, etc. So there's a lot of tools out there that have already been very, very well developed. And then on top of that, the fact that you use code means that you can embed the actual behavior, actual equations, parameterization very easy into your design. But of course, it's harder to learn. If you don't have a coder, if you don't have coding experience, it's of course a steeper threshold to get it. And also, yeah, if you do something in code, you typically need to run the code before you see what you're actually created. And while in a GUI, you have WYSIWYG, what you see is what you get. You have much quicker visual feedback. So quick point and click, etc. But the moment you go to more complex designs, you're going to quickly experience that graphical user interface, graphical design environments on their own have limitations. Which is also why a lot of these graphical design environments contain a coding environment in the background, so which allows you to basically combine the best of both worlds. So there's certain things that you if you make a design in photonics that you want to do in code, there are certain things that you want to do in a graphical user interface, like parameter sweeps with a for loop, or geometries that you need to calculate, or circuit models that need to contain equations, automated routines. You do that in code. Well, in a GUI, like schematic, drawing a first schematic, that's much more easy to do in a GUI. That's like intuitive, drag and drop. Doing some initial positioning for a layout, like floor planning, humans tend to be very, very good. So you can leverage that biological neural network that's in here to do that floor planning. Fixing some final errors, which probably would require like 15 lines of code, but you can just draw a rectangle somewhere in the graphical user interface. That's usually, those are actions where, again, the flexibility of your brain outweighs the flexibility of the code. So that almost brings me to the end of my my talk here. A few things that I want to still mention. If we look at our design flow from left to right, we can also structure that as on a vertical axis, where we basically have a level of abstraction, where at the very bottom you would say that's actually the hardware, the physical design, the geometries that you have, the materials. At the top is essentially a black box that gets signals in and out. And indeed, that's where we start. We start with the definition of a system where we have signals going in and out. And eventually, that's also where we end, because what you do when you test it is you put your device on a test setup and you send signals in and out. And then you have to evaluate what's going on. But you see that as we go through the design process, we go closer and closer to the physics, to the components, to the point where we have a layout that corresponds to what is actually going to be fabricated. And then we go through the fabrication process. So this type of V-shaped design flow is something that you find very, very common also in electronics. Now that means that for us at the circuit level, we basically have, or for circuit designers, we have system level and circuit level. But in general, we don't want to bother too much about components. We typically have the components handled by the fab or by dedicated people in our own organization. Because the moment you dive into component design, you know where you start, but you don't really know where you end. So that handoff between the physical level, the components, and the circuits is, again, what I mentioned, the PDK. So where a circuit designer starts with a set of building blocks that he can use. So he can stay at that relatively abstract level of connecting building blocks together and looking at the signals that go in between. Now, of course, you can go deeper. You can go really to physical component design. And I'm not going to explain all the methodologies of physical component design, but it is true that in photonics today, probably, this is an estimate, more than half of the people doing photonics design are still doing component design. They're still doing electromagnetic simulations to build components. Compared to in electronics, there's many more circuit designers than there are people designing new transistors. Now, why is that? Well, today in photonics, you still have a lot more geometrical design freedom. The fact that you're operating at the wavelength of the light, which is much shorter, makes sure that your geometry, manipulation of geometry, still has a much bigger impact. So things like photonic crystals or inverse design or like optimizing the geometry of an individual building block still makes a lot of sense in photonics. The only problem is that this is typically very time consuming, because now you're diving into electromagnetic simulations, which can take hours or days to do. So it's important when you're designing circuits that you keep this in mind. Don't just jump into this step if it's not needed. Preferably, we're moving towards the same field as electronics, where the people doing this type of work are very different people than doing the circuit design. And indeed, if you look at what we want to do in circuit design we start from something abstract, and the thing that we deliver at the end to the fab is a physical representation of our circuit. So we're basically going down from the abstract to the more concrete. In component design, it's the other way around. You start from some concrete geometry, and in the end you simulate, and what you extract is a behavioral description of your component. which ideally then feeds into the library of the circuit designer so he can use it. Now, there's a whole toolbox of both component design and circuit design tools out there, and I'm just listing a number of vendors here who do provide tools that give you different parts of the design flow, and in some case all the parts of the design flow, but none of them, I would say, and that's my personal opinion, none of them have a first-in-class solution for all the parts in the design flow. So in many cases you see that designers are combining, are mix and matching the different tools from different vendors and combining them together. So with that, I want to wrap up. So Silicon Photonics and photonic circuits are growing towards much larger circuits, and it's not just the technological boundary that we're looking at. We're also looking at a design boundary. What can we actually design inside this technology that allows us to put 1 million components on a chip, but how can we design a circuit of 1 million components that can actually work? And so I explained how we go through the typical design flow. I also try to give you an idea of today what is working well, what is not yet working well. There's a lot of movement in the field, so all these vendors and also research groups in the world that I just showed, they're doing really big steps in improving the tools and improving the design flow. But it's still a work in progress. Now, this was just a 2-hour session. So if you, and of course it's just me talking to you and giving you some idea, but if you want to know more and if you want to get your hands dirty on actual design, there's some opportunities. So twice a year, but I don't have the exact dates yet. In the framework of PhotonHUB Europe, we do organize an experience training. This is mostly focused towards people from industry, where it's a 3-day crash course. You get to design your circuit, we fabricate it and measure it all within 3 days. So you really get like the full cycle, but of course not in very great depth. It's like a bit of taste of all these different activities, but you do get to make your own chip. Now, if you want to do that in more detail, then there's a full 5-day design course, which we normally organize in April. Dates are still to be set, where I dive into all the details that I've been discussing here, but in much more depth. You also get to design your own chip, but you're not going into the clean room yourself to fabricate it. It is being done by service, like most people have their chips fabricated today. And then if you just want to know more about photonics or silicon photonics in general, we usually organize in June a course, a 5-day course, but that's much more high level. It's a big picture looking at the technologies, the application, the design, like the whole pictures. Dates to be announced. You'll hear more about that. Also, if you want to read a bit more about all this design frameworks or the design methodologies, there's this paper in Lasers and Photonics Reviews. It's already like 4 years old, but a lot of the things that are being mentioned there are still very, very valid. Also, a lot of the challenges and problems that we address in this paper are unfortunately not yet fully solved. So they're also still relevant. So if you want to know a bit more about that, you can find that there.